Now let's home in on Earth clones. Let's look at the Earth-like worlds that have been discovered in this science, all in the last decade. This is how an Earth-like planet will form in a simulation. At the bottom you see planetesimals, as they're called, sort of asteroid-sized chunks of material, of which there might be 1,000 circulating around the sun in its early stage. And as time goes by, you can see 10 million years now and moving on, these pieces of rock are still warm and tacky. They stick together by gravity and they form bigger and bigger pieces. And so through this simulation you can see gradually 1,000 smallish chunks of rock the size of asteroids are gradually converted into a small number of Earth-like worlds or rocky planets. In this simulation we even end up with 4 terrestrial planets, not exactly at the sizes or masses of the Earth, Moon, Venus, and Mars, but similar. And it takes about 100 million years for these to form. If we want to see it more visually in a simulation, this is what it would look like. The Earth has not always been habitable, and so one of the lessons of astrobiology is that a habitable planet doesn't have to stay habitable, and a planet that is uninhabitable might become habitable at a future date. We think the Earth will not be habitable forever, too. Here's a distribution, what you see in simulations of Earth-like planets when you follow the water, as well as the rock in the atmosphere. And once again, the Earth is not special in these simulations. If we do the inventory of water as these planets form and evolve, it turns out that having 1 to 10 times the Earth's inventory of ocean water is not unusual, and many of the worlds that form in these simulations have 10 to 100 times the Earth's ocean water. So we think of the Earth as a watery world, the pale blue dot, as making it special, but out there in the universe, in the world of exoplanets, it may not be that unusual at all. And here are the statistics from the Kepler mission of the fraction of stars of all kinds that have at least one planet and what the masses or sizes of those planets are. And it's very interesting. We see that 15% have Earth-like planets, but even more, 20% have super-Earths. That is an object that's 2 to 3 times the Earth's size or mass. Now that's interesting because our solar system has no super-Earths. Earth and Venus are almost twins. Mars is quite a lot smaller, and Mercury is very much smaller. So the most common category of potentially habitable planet in the universe is a category that doesn't exist in our solar system. We also see there are a lot of mini Neptunes, and we don't have any of those in our solar system either. So all of this has led to the question of whether our solar system is truly typical. In the Copernican hypothesis it would be, but it might actually not be. But as far as searching for life, this is all good news because it seems that there are many habitable worlds. And here's the statistics from Kepler, enormous amount of data, where you see the planet radius, and you can see the Earth horizontally marked along with Neptune and Jupiter, and then the orbital period. And so again, Kepler was able to most easily pick out planets with short periods because it doesn't need much data to find a period of a week or 2 weeks or a month or a year. Finding the longer period objects has taken longer and may not be complete until all the Kepler data is reduced. And this is the final result, pending full analysis of all Kepler data, of the incidence rate of planets of a particular size and orbital period. And the box that's missing here is, of course, the Earth clone box, the box most closely matched to Earth size and Earth orbital period. But if you look at the percentages adjacent to that box, it's a fairly good inference that the fraction of all planets that will have a true Earth clone is going to be a few percent, and maybe as many as 5 or 6%. That's a non-trivial number because that's a few percent of an enormous number of stars that could host Earth-like planets. We also have to bear in mind that the habitable zone depends on the star that you're looking at. Kepler and all the people looking for exoplanets have tended to concentrate on Sun-like stars, and you can see the habitable zone of our solar system marked out at the top of this diagram. But if you went down to a dwarf star, of which there are many more than Sun-like stars, so there are perhaps 100 stars like Gliese 581 as there are stars like the Sun, so there's a lot more real estate to look for habitable planets around dwarf stars, you can see that the habitable zone shrinks inwards because the luminosity of the star is less, but we can still find habitable planets. So the habitability, of course, depends on the nature of the star and the distance of the planet from the star. It also depends on the atmosphere of the planet, something we don't always know. Here's a magnificent system just discovered a few years ago, the TRAPPIST-1 system. And you can see here, by comparison to the inner solar system, an incredibly rich set of planets, at least 3 of, and possibly 4 of which are in a conventional habitable zone. So again, while the Earth is the only planet in the habitable zone of the Sun, here's a system recently found with 3 and maybe 4 habitable planets in one system. This is a system that people have looked at in great detail, and we can see the orbital parameters, size, radius, mass for all the planets. This is a system which, if you conclude the unconfirmed planets, has actually more than 9 planets. So it's richer than our solar system. Since Pluto was demoted, we only have 8 planets. And in detail, there are fascinating connections in the orbital periods. We can see that the ratio of the orbital periods, the second bottom line, shows that there are integer ratios. These are harmonics. So orbital periods sometimes line up due to gravitational interactions in harmonic ratios, that is, the ratios of integer numbers. And that suggests a musical analogy. And so here we have the TRAPPIST-1 system turned into a musical analogy. And now we come full circle with what we talked about very early on with the ancient Greeks, the harmony of the spheres. Here's a system where you can actually literally imagine that based on the harmonies of all these newly discovered planets. And this is what it would sound like. We'll put it on a clef first, and then we'll listen to it. Kepler would have got a kick out of that, I'm sure. What's the next stage in the discovery of exoplanets and their exploration? Well, they're too far away to explore. So the next stage is trying to inspect their atmospheres to look for signs of modification of the atmosphere due to life. This is called the biomarker experiment. Here we see the spectra of the inner solar system of our solar system showing what the atmospheres look like. And you can see that Mars and Venus and the Earth all have a carbon dioxide signature, very strong in the spectra. But the Earth, and only the Earth, has water vapor and this very strong ozone feature, which you can see at a wavelength of about 9 microns in the infrared. Oxygen and ozone would be telltales of life because all the oxygen in the atmosphere that we breathe was produced by microbes billions of years ago. So, reversing the logic, if we see oxygen and ozone in the atmosphere of an exoplanet, it's very strong indirect evidence of microbial life. So that's the experiment that astronomers are trying to do. It's going to take a next generation of space instruments and large telescopes on the ground to do that experiment, because an Earth-like planet, like the Earth itself, only reflects 1/1000th of the sun light to the telescope you're looking from, seen from afar. So you have to either squash the starlight by a factor of 1 billion or suppress it in some other way to see the feeble reflected light and then smear it out into a spectrum. It's a very difficult experiment, but it can be done. And we'll be looking, of course, at all sorts of biomarkers. Oxygen and ozone are good ones, but also methane is a biomarker, and yes, we would want to see liquid water, of course. And what are these Earth-like planets going to look like? Well, they're going to be subtly and maybe even profoundly different from the Earth, even if they're habitable. They may not have chlorophyll, they may not have the same color of their vegetation, the sky may be different, there may be multiple stars or multiple moons visible in their sky. They will be bizarrely different and yet strangely familiar if they have liquid water. And the bad news is the nearest of these Earth clones is likely to be dozens of light years away. That is hundreds of trillions of miles. So finding Earth 2.0 will not obviate us from the need to take care of Earth 1.0, because these Earth clones are so far away we'll never go there and we'll never be able to escape there if things go wrong on this Earth. So we can see potentially habitable planets, and in this work from the University of Puerto Rico, we can characterize a planet in terms of its habitability index on a scale of 1, where that's the best of all possible worlds, perfect nirvana and Eden, and 0 is uninhabitable. And in this scale, you can see that there are planets that are more habitable than the Earth and way more habitable than Mars. So there are these planets, and the closest of these is Proxima Centauri b. You can see on the top left, 4.2 light years. So very exciting that a potential Earth clone is in the nearest star system to the Earth. We also have to remember that this habitable real estate, in the conventional sense of being close enough to a star or at the right distance from a star to have liquid water on the surface of a rocky planet, is underestimating the total habitability, because we also have to include that cryogenic biosphere that's out where moons of giant planets might be and might host life. We also have to remember that these are only planets we're talking about. I've talked about the possibility of moons in our solar system hosting life, and there are now 4,000 exoplanets. What about moons around those planets, or moons in systems of other stars? We have not detected a single exomoon yet. It's a very difficult experiment. And so we cannot find equivalents of Europa or Titan or Enceladus yet around other stars. That's for the future. So we're underestimating the amount of habitability for sure by only looking at Earth-like planets. On the right here, you also see a category called nomads. It turns out when you simulate the formation of solar systems in a computer, very often Earth-like or habitable planets are ejected from the system in the first few million years or tens of millions of years out into interstellar space. Now, if they have thick atmospheres, they can be self-contained biospheres that don't need the radiation from a star. And so these free-floating planets with no parent star are essentially impossible for astronomers to detect right now. And yet simulations say there might be as many nomads as there are Earth-like planets. Another exciting possibility for the future. And we can imagine what the young Tycho Brahe and the one young Giordano Bruno might have made of all this work on planets that they could only dream of.
Dude, this is awesome.
Definitely. Awesome.
I mean, like, all those stars. Dude.
Oh, there's millions of them.
And like each one of those stars is like a sun.
Like, whoa. Dude. That means that, like, oh, there's tons of other solar systems.
Well, yeah.
Whoa.
And that means that we're like
little specks. Oh, like almost nothing.
whoa.
Let's do the inventory of habitable worlds. Here they are. Look at the finger with wet grains of sand on it, about 300. Each of those is the habitable worlds in the vicinity of our solar system, within maybe 100 light years. And that's the stuff we get to work with. Those are the objects we can study with our best telescopes. And we remember that if you zoom in on a grain of sand, it is indeed a tiny little world, each one with its own origin. Often they're former living creatures, of course. And so we are reminded of the words of William Blake, the poet, to see the world in a grain of sand and heaven in a wildflower. So they're not just grains of sand, they're worlds. And those are the 300 or so we can study with our big telescopes. But they're representatives of a huge number of habitable worlds. Extrapolating the work of Kepler and exoplanet discovery to this point, we project a number of about 10 billion habitable worlds in the Milky Way galaxy. And that's analogous to the number of grains of sand in the sandbox. A prodigious and almost amazing number. Almost too much to get a sense of. So if we want to get a sense of it, let's look at this little travelogue where we imagine a trip that we can't really take to each of these in turn. 5 seconds for each planet, and then move on to the next one. Let's just enjoy it for a little bit. If we were to visit all these habitable worlds in the travelogue you've just seen, that was about a minute's worth or a dozen of them. If we were to go to every one and put it together in a travel film, you'd be sitting and watching it for 10,000 years. That's the prodigious amount of habitable real estate in our galaxy. But also we have to recognize that the universe is filled with 100 billion galaxies, and there's nothing special about the Milky Way. So to ask the question of how many habitable worlds, places that could host biology, any one of them, or all of them, in the universe, it's 10 to the power 21. That is 1,000 billion billion, a truly fantastic number. And so you can see probably why astronomers think it's very unlikely that we are the only biological creatures in the universe. We can listen to the slightly jaundiced words of Thomas Carlyle, Scottish historian. If they be inhabited, what a scope for misery and folly. If they not be inhabited, what a waste of space. That's the end of this topic.